So, hope you're all doing well. And sorry for the one that I scared at the beginning. But yeah, so I'm Ahmed Mari, co-president of the Mathematics Society, Loredana. Yeah. And today, it's going to be our last event of the Mathematics Society for this semester. But not random event, but the fourth edition of our undergraduate seminar. So I see some new faces here. So let's talk first about So let's first talk about what's the undergraduate seminar and what does it really mean, right? So originally, the undergraduate seminar was an old module that math majors had before. Before that, Jacobs University went to Construction University. But then, with this new edition, Construction University decided to remove this model from math majors. However, our old president, Omar, decided to bring back the undergraduate seminar and make it something I would say recurrent in the Math Society. So we decided to revive it. But how? And what's the concept? So usually, math students apply to get accepted to do the undergraduate seminar. Those students get accepted, conduct a 2 weeks research with us, the supervisors, and the professors, namely, most likely Professor Ivan. Then, when they're done, and they present the research today, their research papers get reviewed afterwards by the professors, mainly the math faculty, etc., etc. They present their audience in front of you, and hopefully you want to read their papers afterwards, and so on and so forth, and it gets officially published, part of the construction journal. So, of course, this is not going to be the last edition. We're preparing to hopefully continue it for our next semester. So if any of you want to apply for it maybe and conduct its own research and have its own official paper, don't hesitate to apply. Because at the end of the day, that's the goal of the Math Society. Make mathematics affordable for any person at the university, right? So let's talk about our seminarists of the day. So we have Tanya, first year computer science major, that was talking about how the Ranskota method solve differential equations in the modern neural networks. Then we have Mariami, our second year physics and data science major, that's talking about dark energies and the acceleration of the universe. And last but not least, Rakan Khatib, the first year, surprisingly, IEM major, that is conducting research on Belfort's law and how can we use it to detect false accounting reports around the world. So I hope you're all ready for these talks. Of course, if you would like to join our WhatsApp or Instagram, or even apply for our next UGS, don't hesitate. And be ready, because in a few minutes, we'll start our first talk, given by Rakan. Thank you very much. Thanks for your presentation. Let's see. Let's go to it. We'll do all stuff. I would bugs. ليش أطول؟ I thought you did. We did. No. PowerPoint. Sport. Would it be a problem? Would you have an opinion?
You should just do it for games. Pretend that we're prank.
See, that's why I wanted to do look. Normally when it's downloaded, it's automatically like you can take here and the other. Must be a way to do it.
I had a freedom to.
Do you have the PowerPoint?
PowerPoint, yeah.
I did it to her. No. You're the truth. Yeah. No, it's
I actually have.
it's obvious.
Like, I mean, it's he has a good rhythm. See what? What is suddenly today? No.
That's
I mean, like, it's been.
you have automatically
I'm sure in the week before your big presentation, you suddenly developed arrhythmia, and it's not just nerves.
go first.
Seems like they're having trouble with this.
It seems like they're having trouble. Maybe you should just get it over with.
Take it to the other screen and do present there. Right.
What are you saying?
Do I?
You're not gonna. You say that every time, and you still do really well in the oral quiz.
Present it. That's really look at it.
I wish I misheard my
Just the minus sign. This one. It's actually quite.
Sorry, but
Hello everyone, my name is Rakal Khatib. Today I will be explaining Belford's law, a hidden pattern in numbers. So, before we start, I would like to ask you guys a quick question. If we chose 1,000 Twitter accounts at random, how would the distribution of their followers look like? A concrete example would be like, if a Twitter account had 784 followers, too late. If a Twitter account had 784 followers, okay, its leading digit would be 7. So in the distribution, we would add 1 into the 7. Now, would you say all of them would have the same distribution from 1 to 9, or would you say one is more likely to have a higher probability? Now, logically, your brain would say that there's no reason for any number to have a higher probability than anything else. And as you can see here, each number, 1 has 11.1%, 2 has 11.1%, so on and so forth. Now, this is how our brains would look at it, and unfortunately, that's actually wrong. And this is all wrong according to Benford's law. Benford's law explains that 1 has a much higher probability, whereas 2 has lower, and then 9 has 4.6%, the lowest. Now, why does this happen? It's based off a logarithmic relation. Now, to get to it, you have to understand the basics. So let's start with the history. In 1881, astronomer Newcomb. Before we had Twitter accounts, before we had calculators, all of those types of stuff, astronomer Newcomb was going through logarithmic pages because that's how they used to they used to store the logarithmic distributions. And as he was searching through them, he realized that logarithmic tables that start with lower leading numbers like 1, 2, or 3 were used much more frequently than logarithmic tables that were used higher digit leading logarithmic tables like 7, 8, and 9. And this showed that there was more frequency while using them from wear and tear, fingerprints, creases, and he tried to come up with a conclusion that this is based off a logarithmic relation. And he tried publishing it to the world, but unfortunately it just disappeared with time since it was just theoretical. Now, in 57 years later, in 1938, physician Benford came with the same theory of astronomer Newcomb, and this time he actually made observations and tried to put it in concrete formulas. And what he came up with is that it does follow a logarithmic relation, which is P of D, and D being the number of the digit, follows the formula of log base 10, 1 plus 1 over D. Now, what does this essentially mean? This means that, let's say, for example, you have 1. So you put 1 plus 1 over 1, that's 2. So log base 10 of 10, log base 10 of 2 would be 0.301 or 30.1%. Now all of this, throughout all of his observations of 20,000 different observations from all different types of categories, from digitalized aspects to weights, he actually made it concrete, and that's why it became known as Benford's law rather than Newcomb. So let's look at Benford's discovery. What actions did Benford take? He rediscovered Newcomb's forgotten observation. As we already said, Newcomb theoretized it. He tried to say it is, and he guessed what it was, and he was correct, but he couldn't put into concrete solutions. And as we said, he tested the pattern across 20,000 observations. Now, the data sets he analyzed, river lengths and geographical data. Anywhere from, for example, if I were to give you, if you were to name me any random river, it would have a 30% chance of the leading digit starting with 1. Unlike with a 9, it would have 4.6% chance. And this happens with a lot of stuff. Atomic weight, stock market, population statistics. The list goes on and on. It's everywhere around us, and we don't really realize it. Key finding, as we already said, digit 1 appears 30% of the time, approximately 30% of the time, while digit 9 appears only 4.6. Here we can see the mathematical formula, and it has two invariances. It has scale invariance and base invariance. Now, scale invariance is, for example, if I want to use Benford's law to have cities population. Now, what it means is I can multiply it by any positive constant, and the outcome will still stay the same. So let's say there's a city with a population of only 1,000. I need to increase the magnitude to go in depth. I can multiply it by 1,000 just to make it to millions, but the answer would still be the same. Base invariance. Now, base invariance means that Benford's law adapts. It doesn't have to be only 10 digit. It can be it can be 15, it can be 20, it can be 1 million. It will give you the probability of each. Now, this works for everything as long as the base is greater than 2. Now, how we see if a natural distribution follows Benford's law is by a chi-squared goodness of fit test. Now, what this test essentially is we predict what the distribution would look like if if it did follow Benford's law, and then we solve the distribution of how it actually is. And then if it deviates a lot, then there would be something irregular. Now, if it does follow and have the symmetry of Benford's law, then we can say that it does follow Benford's law. Conditions and where it applies. Now, we can see Benford's law all around us, but we don't really realize it. And its conditions they're simple, but they can have a bit of fluctuations. For example, we have the perfect conditions would be it would span multiple orders of magnitude. We're not talking 100 to 200, we're talking from 1 to 1 million. And then we have multiplicative or exponential processes. It needs to be multiplicative, it can't be additive. I can't add numbers together and then explain by Benford's law. Natural or manipulated data sets. Anything we make ourselves, since humans are bad at trying to make random patterns, it wouldn't work. And then large data sets with scale diversity, we have to test it with multiple sorts of categories. And then where Benford's law apply, here we can see finance and commerce, natural sciences, digital age, and the list goes much further. We can see it with a lot of different stuff as well. Now, a cool example of this, for example, would be physical constants. We can see it with even light years. Earth or nature tends to really follow Benford's law, and we can see it when it comes to gravity, light, speed of light, speed of air, speed of gases, speed of sound. So so nature does tend to follow Benford's law, and it's not this random chaotic thing that just happens constantly. Okay, important exceptions. Now, as we said, so it has to be with multiple orders of magnitude. So narrow ranges like human heights, 150 to 200 centimeters. For example, a human would usually be 150 to 200 centimeters and would rarely be over that. And now, if I were to get all of your heights and put them in a distribution, 90% of you would be at 1, and then maybe the 10% would be at 2. That does not follow Benford's distribution at all. And then the same thing goes with IQ scores and standardized test results. And we have uniformly randomized numbers. If we choose randomized numbers, then Benford's law doesn't follow the pattern of Benford's law. And then we have data with artificial constraints. We can't get a distribution and then put some ranges on it or put a specific constraint, because then it wouldn't follow Benford's law. Data quality challenges. Now, this is really important. Benford's law can really start to mess up, especially if you start rounding numbers and have truncation. Now, if you are testing Benford's law, you have to keep it as the data goes. If you get 19.8, you can't round it up to a 20, because in that case, it will stop actually matching Benford's law. And this will be important later on when I explain how it's used against fraud. Digitization, artifacts, recording mistakes, data processing, noise. This is all normal. Applications and validation. Okay, so forensic accounting. If let's say I had a restaurant, okay, and I wanted to money launder or I wanted to use fraud. a way the government would see if I was using fraud. So let's say I do change the receipts or the invoices or increase my revenue. This the pattern stops following Benford's law. Now, although this might not be proof that I'm money laundering, it's the big warning sign, it's a big red flag. Until now, it is used in many countries, as well as Germany. We have tax auditing, same exact concept, and data validation as well. Empirical validation. So we have population statistics follow the logarithmic curve, and I've actually done an experiment here in this university that we'll get into, and we will see how population statistics actually do follow Benford's law. And then scientific constants, as we said, speed of light, whatnot, financial records. Financial records must match the distribution. So when it comes to us humans trying to decipher our invoices, increasing our revenue, just to get away with tax, as if the financial records don't follow Benford's law, then it's a major red flag. Okay, so to the experiment I did. I was in the IRC. I was making this PowerPoint actually, and I decided to come up to random people and ask them which city they're from. So after I asked which cities they're from, I collected all the data I've got, and I counted the populations of each city, and then I distributed them into the leading digits. Now here we can see. Now here we can see the distributions. I got over 80 countries from 116 people, and even though that's not a large scale, we can still see that there is a resemblance of Benford's law, where 1 has a really high distribution compared to 9 having a really low distribution, and that just shows even when you don't have a big scale, Benford's law is there. It's in the process. So whenever you look at a number, whenever you look at stocks, at anything, just know Benford's law is doing some work in the background. And that's it for today. Thank you very much.
Any questions?
Any questions, guys? Yeah, Manny.
For the y-axis on your graph, what was the proportion on?
It was, I counted 116 people and I divided by 40.
How would it work with stock prices?
Okay, so stock prices, for example, have you ever heard of index funds, how stock prices go up by percentages? Now, when stock prices go up by percentages, let's say it goes up by an average of 1% every day. We have a stock price at $100. It goes up by 1% every day. Now, at the beginning, it's at 101 and then 102.1. Now, it's gonna go up, and at some point, it's gonna get into really big numbers. And even when it does get into really big numbers, the numbers after each calculation, 30% of the time would start with 1 rather than starting with a bigger number. And this works with everything. So if you can even try it out yourself, you can get a calculator and put a random number to the power of 2 or 3 and start saying the answers you're gonna get. You might get 8 million the first time, and then you might get 20 million, and then 30 million, and then the answers just keep going and tending to follow the smaller numbers rather than the big numbers.
Thank you so much.
Any more questions? Thank you very much.
So, thank you, Rakan. Please, again, round of applause for Rakan, guys. Come on. So again, thank you very much, Rakan. That was a very, very good talk. And I was able to witness the work that Rakan put in his research for the past weeks. And I'm very proud of the talk that I was able to do today. So we'll have a break of, I would say, 5-10 minutes. And be ready, because afterwards, we start our second talk of the day that's given by Mariami about dark energies and expansion of the universe. Thank you very much.
Could you? I have a question for you. Ask when we're outside.
هو مزيان ما خصهاش ما كانش خصو يمشي غير يفهم الكبار جيت فيها كثر من التكست زعما مغربي فلسطيني فلسطيني Nice presentation.
Thank you so much.
Congratulations.
Thank you so much. Finally, خلاص it's like it's out of my system now.
I took great pictures.
Thank you so much. I'm so done.
واحد هو كيجبر ماشي مستعد الفيلم.
Thank you so much. Thank you.
Never let the never. Never too late the never. How's it going?
والله
Is there a comment? Okay, okay. You bro. Because الشارع قبل ما تسوج اش كامل الشمع
Basically, some
قلت لي دوسو كامل عارف
for lots of goods.
ديك سميتو
You got it.
فيه مناطق في الماضي بزاف وفيش
سمية سميتها how to solve differential equations in linear science.
وي شي زبرت كانت نورمال درت فيك نورمال ودي بعد
We'll come now.
Yeah, okay, what do you
هو الفيزيكس مثلا فين هي دابا هادشي هي علمنا المهم قلت لك هي ممكن تكون هي الاولى ولا الاخيره
حاجة ما تخيل.
فين الوصيه ديالك
شكون لي الصح
طيب جيتي تسالينا التوك الاول ولا التوك الثاني تريح صافي مره ولا خليتها لك مره ثانيه صافي دوزت
Semester again.
حتى زوينة.
Program has two courses.
Are you crazy?
I had to.
You know, it actually hurts.
I have to. You're sitting in front of me.
خرج فيك لاك زهري يا صاحبي.
شاتو
جبت خرجت اخي كاس. I have to
شاتو
stay minutes.
understand
I have time. Here, I'm done with the first question, but okay. Further down.
President. What's going president? What's calling professor?
Oh,
Sorry, if you call me president, what's you call me professor?
Because you're both professor, Mr. President.
Thank you very much. I miss you.
He answered like, and then when he answered, I was outside. So
City center?
Yeah, no, it's. Sometimes you can just go.
Sometimes, yeah, sure. But 40 minutes.
40 minutes. No, we can go with. I think an hour plus something.
you have to think about it.
Is it like a pool of Bremen?
Yeah. And I went there and she said that it's good. Yeah, shit is very good. This pool is basically for Sicherheit, so it's for security. And they just partnered with the university.
Oh, yeah, sure, I know. But it's very good pool, to be honest.
Yeah, it's very good, but there it's nice. So and
It's a pretty good pool, to be honest.
yes, I like it.
I should have done that, but
I want more.
I didn't think about it.
I want it to be open on Sunday,
Yeah, I understand. I feel the same, to be honest. Of course.
Very good job.
Oh, thank you so much.
How many time?
15 minutes. Oh, no.
For preparing.
For preparing the presentation, it took me like maybe 5 hours. In general, I'm really bad with PowerPoint, but the research took me like a whole 3 days.
And who do you write it with? For which professor?
No, just me. Self-taught. Thank you so much.
I haven't heard about it. I mean, right?
Yeah. No, it's honestly quite amazing. It's really interesting, especially once you get into it. If you want, I'll send you your research paper after. It gets like deep into it.
You do it like in latex then?
Yeah, later.
If it's possible.
Yeah, okay. I might finish it in the next week or so. And for sure, I'll send it. Right, thank you so much. Pleasure to meet you.
واحد وعشرين اور صور الصوت 21
Yeah.
You were there also.
واش عندي شنو يقول لي
Yeah, it was last weekend, right? Last to last.
Was in the beginning.
Yesterday, another hackathon.
عشان كذا قرايت ساعه كامله
It was about
And so about this.
No, I know that's why I didn't register for this program because I had to miss it.
That you will.
They allowed when I.
لا انا في لوكي واحد يقول لك صور
Yeah, I need that. I need that.
جبت في كندا كان يعطيها فلوس معك ما يمشيش نتوما لا لازم مزيان عرفتي شحال هي حط اول حاجه Do you like this program? علاش ابغيتي
Yes.
نسيتينا بروجي انا خاطر نسيت
I think it's easy for you.
Much easier than MSCS. Much easier. It's nothing compared to MSCS.
Why don't we study together?
Problem solving.
outlook
Prove this group. I was with Alex yesterday. I did the latex. I did the first one. The second one, I was.
I saw you
which one
in explanation.
I get 46 for this exam. I will be happiest.
واحد شويه يقول لي
Pass.
No, you gonna.
Yeah.
It means you're gonna be zero in complement.
كم كلشي ما قلتش
It means 100%.
100%. Get a zero.
Yeah, if you get a
It means
zero, it means
100%.
100%.
If you get a 5 out of 5, it means like you failed.
Yeah, but they have one is the best, no? Not
It's zero.
zero.
Yeah. It's in the grading system.
It was the best.
Just one.
Being a positive.
Ah.
Oh boy.
Practice things. C is fine. You just practice things.
See, it's fine.
يقول لي
For me, it's better because I mean, problem it's not
We have changed the
maybe in
chip
the
system.
perfect world, you know.
Okay, it's a grade of 1.
acceptable
1 is the best.
One is
And I think 0. No 0.
you know, you're thinking like computer scientists. You starting from zero, you know.
I still not have that knowledge.
عطاني سورتو
Oh my god.
عطاني تيوريك ما كوديتش
She's not the.
I know that she would.
Yeah.
She was.
قالوا لي
I asked him if I
له بوتنسيال ممكن
take the attempt.
دابا لي بروفيسور كيشوفوا الابليكيشن ديالك كيشوفوا واحدين واحدين لا
And he was.
وما راه ما عرفتش سميتو
Failing.
انت اللي تكون بغيتي شكون ما بغيتيش فهمتي
The exam. He was saying,
يا راه
if you
ممكن
fail, and if you fail.
ممكن لا وهذا البروف بالضبط اجا قال لي
Interview the internship.
توشي
Professor,
Keep it as a character.
فيكشن بيرس
Professor is like he's you know he did research in the Bell Labs. The Bell Labs is the did
I want to connect with you in interview. Are you free؟ قلت له لا. لا قلت له هو اللي ما يقصر. قلت له لا. قلت له شو كاين السيبان؟
I think it seems like he has
ليش قصتاني؟ الاثنين يقول لي free yourself right there هذا
he already seen so much in his life.
myself.
He just he just wants to
Yeah.
انا كيف نشوف معك
I can like
كتعرف شي
with king.
شي حاجه زعما
Mine is gonna
ترى
and
هني انا سيت كتبين ماشي حاجه هني انا سيت ليش قبل تعرف
I can
يلا
good yeah. Good person.
بكل صراحه ما ديتاي ما حتى كنخسر في ديبي سبتمبر 3 شهور دابا كتبت 3 شهور
وراه ملي سافرت البروفيسور راه
5 minutes.
ما عقلتش
Like presenting.
دخلت لانترفيو والله ما عرفت اليونيفرسيتي اللي كيقرا فيها هو
وانت مش معك ربع ساعه.
كان كيتكتب بالسلبه
You speak very Hindi.
no I don't speak Hindi.
شويه
You missed it.
كينغا
عطاك شي اكزامبل.
No, this is epic. How she learned it? I was barely able to learn it. See, it's gonna watch FIFA and all that. That's but
كيفاش كان كيشوف والله كيفكر قال لي شنو عندك داز على السي في ديالي قال لي دابا في السي في شرح لي
no.
كيف كان كيلاكي وبقى كيسمع علي قالت لي واخا
which was
دير انترفيو والله ما عقلتش واش حنا عقلت انا بتانيه والله ما
that I'm coming here.
But it had like 150 pages of
داز على السي في ديالي قال لي
650 pages.
شوف بدي واحد الانترفيو بدات الصيف اللي فات قال لي شنو درتي فيها انترفيو بدات الصيف
No, it's like
درتي فيها قلت درتي فيها شرح لي
he's like the emperor. He's struggling. He has to have a word with his enemies, and he's very unsure what he should do. He's hesitating, some hesitant, and the character he has like Hindi. He helps him overcome this. It's like a very life story. It's like an epic, but it's real life.
It was an experience.
Yeah.
So hello everyone. So hope you all liked the first presentation given by Araka. And now we move to the second presentation of the day, namely given by Mariami about dark energies and the acceleration of the universe. Please a round of applause for Mariami.
Hello, I'm Mariam, and today I will talk about dark energy and accelerating universe. So first, we'll talk about the first observational evidence of the expansion of universe. Oh,
Sorry.
oh, okay. No.
Go back, go back. Yeah.
Okay.
Take your time. Okay.
So we'll talk about the first observational evidence of the expansion of universe. In early 1900s, the scientists analyzed the spectral lines from distant galaxies using the spectrograph. A spectrograph is an instrument which disperses lights in components, and by analyzing those components, we get the spectrum. The spectral lines are colored or dark lines, which corresponds to the emission or absorption of photon. Now, when electron jumps from higher energy level to lower energy level, it emits a photon with specific energy, and that is the emission, and it corresponds to the colored lines. And when atom absorbs the overall specific energy, its absorption, and it corresponds to the dark lines. Now, the positions of spectral lines are unique to each chemical element. So scientists just took the emitted spectral lines, they compared them to the laboratory spectra for different chemical elements, and they observed that the spectral lines were systematically shifted to the longer wavelength. And that is called the cosmological redshift. And cosmological redshift led scientists to speculate the expansion of universe. Now, as we can see, this is the example of cosmological redshift. Those are the absorption lines, and they are systematically shifted to the redder or longer wavelengths. Now, if universe was expanding, then light traveling through the universe would also stretch, and that would explain why they observed the cosmological redshift from the distant galaxies. This phenomenon also led to the Hubble's law, which shows us how the velocity of expansion of universe is dependent on the proper distance between the galaxies, and this was. After this, there were many observational evidences that the universe was expanding, but this was the most fundamental, first one, which led scientists to formulate mathematically the expansion of universe. Now we can move to the mathematical framework of universe, and let me introduce the Copernican principle. According to Copernican principle, that matter is evenly distributed in the universe on sufficiently large scales, which means that the local fluctuations in densities are averaged, and this also implies that the universe is homogeneous and isotropic. Now, in order to more deeply understand what homogeneity and isotropy is, first we have to mathematically conceptualize the universe. So, mathematically, a universe is a four-dimensional manifold where each event is described by 3 spatial coordinates and 1 time coordinate. And manifold is topological space, which locally resembles the Euclidean space, which means that locally it is flat. And now we can define the isotropy and homogeneity. Take an arbitrary point on the manifold. If the properties of the space are same in all directions, then the universe is isotropic. And if the properties of the universe are same everywhere, then the universe is homogeneous. So in order to geometrically describe the universe, we have to choose a parameter which will be invariant under the changes of coordinate system. And such parameter was found to be a space-time interval. A space-time interval describes the distance between 2 infinitesimally close events, and as we already said, it is invariant under the change of coordinate system. And this is given by this equation, where c dt is the distance traveled by the time. And for the standard universe, the space-time interval is rewritten as this. And here, the sigma square is the spatial part of the space-time interval, and AT square is the expansion coefficient, which describes the expansion of universe. And now our next goal is to find the spatial line interval for 4-dimensional manifold. And to motivate how we derive the formula for spatial line element, first we will derive it on flat surface. So distance between 2 close points is given by this equation. And if we use the Cartesian spherical coordinates transformation, which is given by the systems of relations, if we differentiate them with respect to the spherical coordinates and plug them in this equation, we will get the spatial line element. And this spatial line element is for flat surfaces, and now we want to generalize it for curved spaces. And in order to do that, we will introduce the curvature parameter k, which describes the intrinsic curvature of spatial slices. And we can have three possible values for k. For k equals to -1, we have negative curvature and we have the open surface. For k equals to 0, we have zero curvature and, well, we have just a flat surface. And for k equals to 1, we have positive curvature and that is a closed surface. And finally, our spatial line element can be rewritten as this equation. And if we plug this in a space-time interval, we will get the FLR metric. And this equation, which shows us the distance between two closed events, can be rewritten as this equation, where GMV is the metric which encodes the geometry of the universe. So now we have done all the mathematical stuff for the universe, and now we can move on general relativity. And so first, we are going to see how the free-falling particle moves in Cart's space-time. But in order to do that, in order to motivate how we're deriving it, first we'll introduce how the free-falling particle moves in flat space-time. And for that, we are going to just write the Newton's second equation, that the net... I don't know how that works.
On the left.
Maybe you have to
Press the button
to
on
press the
left.
button in.
On the right.
No, on.
And the left on the screen, the middle.
Oh, that's one?
In the middle of the left.
Oh, thank you. Yeah, so we'll write the Newton's second law, the net force is equals to ma. But if we have free-falling particle, then F equals to 0, and we will just have that ma equals to 0. And the simplified form of this equation is given by this expression, where x mu is the space-time coordinate, where mu changes to 0 to 3, and lambda is the affine parameter, which we use to parameterize the path. And now if we use the chain rule, this can be this can be written as the combination of partial derivatives, and we call this coordinate basis vector. And but it turns out that this equation is only true for is only valid in flat space-time, because in curved space-time the coordinate basis vector changes depending on the position of the vector. So we can see that from here. As you can see, each coordinate basis vector changes its direction and value. So to address this change, the covariant derivatives are introduced. And we are going to replace the partial derivatives with the covariant derivatives, which takes the change of basis vectors into account by introducing the Christoffel symbols. And the Christoffel symbol is mathematically given by this expression, where G is the metric of the universe, and it describes how the coordinate basis vector change on Cart's space-time. So this is our final formula, and this tells us that the free-falling particles on Cart's space-time moves on geodesics. Now, geodesic it describes the minimal path between two points. So it basically is a generalized straight line for Cart's space-time. And now we can move to the Newtonian limit. So now our goal is to observe how the general relativity reduces to special relativity within the Newtonian limit. So the Newtonian limit makes three assumptions. The first assumption is that the particles move slowly compared to the speed of light. The second assumption is the gravitational field is weak, which means the metric can be decomposed into flat space-time and small perturbations caused by the gravity. That means that if we have like a flat space-time, like small fluctuations is only like from the gravitational field. And this is given by the equation here, where G is the metric of the universe, and the first term on right-hand side is the Minkowski metric, which is given by this matrix, and it describes the geometrical properties of flat spacetime. And the second term on right-hand side shows the metric encoding the perturbations caused by the gravity. And the third and final assumption within the Newtonian limit is that gravitational field is static, which means that it doesn't change over time. And now if we use those assumptions, and the geodesic equation can be simplified to this equation. And if we compare this equation to the equation for Newtonian gravity in the flat spacetime, which is given by this expression, if we compare those two equations, we will get that h00 equals to minus 2 times phi, where phi is the gravitational potential, and h0 is time component of the metric, which describes the fluctuations caused by the gravity. And now let's see what this equation actually means. This means that the gravitation is itself encoded in the metric. So if we have gravitation, then we have the curved spacetime. And this is really crucial for other equations too, so keep this equation in mind. And now let's move to the next part, where we are going to generalize the Poisson equation for Newtonian gravity. So for Newtonian gravity, the Poisson equation is given by this expression, where this is the Laplacian of the gravitational potential, and this is the matter density, G is the gravitational constant, and this equation tells us that mass density acts as a source of the gravity. So if we have a mass density, we have the gravitational potential. Now, in order to generalize this equation for general relativity, we have to, well, of course, generalize the mass density and the gravitational potential. So to do that, yes, so let's first work on the matter density. So we know from Einstein's equation for special relativity that E equals to mc squared, which means that the mass and energy is interchangeable, and if the mass density is a source of gravity, which we can see from this equation, then its generalization should take contributions from all forms of gravity into account. And to do that, we are going to introduce the energy momentum tensor, which is given by this tensor, and each component describes the flux of muth component of form momentum through a surface of constant xv. So for example, the first component of the tensor describes the energy flow, and the diagonal ones describe the momentum flux. And so the result of this is that the energy momentum tensor contains the contributions from energy and momentum density, pressure, and stresses, and that's what exactly we needed to generalize the Poisson equation for general relativity. So now we can move to the to the gravitational potential. And as we already saw, the gravitational potential is, if we have gravitational potential, we have the curved spacetime, so that we can take a guess, and you can say that we need the tensor, which contains the partial derivatives of the spacetime metric, because our equation for h00 was minus 2 phi. And those tensors should be also considered geometrical properties of energy momentum tensor, and such tensor was found to be an Einstein's tensor. And here, this term is Ricci tensor, and the second term is the Ricci scalar. Now we will explain what each of them are. So let's say we have a curved surface. Okay, let's just first let's consider a flat. let's say we have a flat space-time and we have a closed loop. If we take a vector with some angle, that doesn't matter. But if we parallel transform it along this curve, the direction of vector won't change. But the direction of vector changes when we have a curved space-time. So the Ricci tensor describes how the volume of shape changes when moving along the closed loop, around the closed path on the curved spacetime, and the Ricci scalar is just the average number of curvature for the curved spacetime. And so far the equation looks like this. The Einstein's tensor is proportional to the energy momentum tensor, but however, it was observed that the universe is accelerating, which is due to the dark energy, and to take the dark energy into consideration, we will introduce a cosmological constant, and after adding the cosmological constant, the final equation for Einstein's field equation for general relativity looks like this. Yes, where these two terms describes the geometrical properties of the curved space-time. This describes the contributions from dark energy, and this is the energy momentum tensor. And this equation once more tells us that if we have the matter density, we will have the gravitational potential, which is also a result of curved spacetime. So now we have all fundamental concepts from general relativity, and now we can move to the Friedmann's equations. And once again, those are the equations we are going to use to derive the Friedmann's equation. The first is FRV metric, which describes the distance between two closed events. And the second equation is the Einstein's field equations for general relativity. And the third equation is the energy momentum tensor for perfect fluid, because we're considering that the universe acts like a perfect fluid because it's homogeneous and isotropic. So using those three equations, you can get the final Friedmann equations, and those equations basically tells us how the expansion coefficient changes over time. Those are differential equations, but if we solve them, we'll get how the universe was expanding over time. And thank you for your attention. Questions, feel free to ask.
Other questions?
Yeah.
Is there any possible practical part of this is pre-abstraction? This talks about like the abstraction, the universe, and everything. Is there like any domain in our real life where we use such calculations?
Real life sorry, what? Real life application?
Yeah.
Not like everyday application, but we're that's a good question, but yeah, I don't know the real life application, but it describes how the universe is expanding, and that's quite important information. We're living in it.
Thank you very much.
Thank you for listening.
So, hope you all like the talk given by Mariami. Please, a round of applause again for it. Come on. So, be ready, because in a few minutes, we'll start our final talk of the day and final talk of the semester, given by Tanya, about Tranche-Quota methods, and we can use them to solve differential equations involved in neural networks. Thank you very much.
You could, bro. Please don't do this. We used to do this in India.
don't know.
It's really good. I mean, even like the little stuff you cook on the board or whatever, that was like nothing. That was
Crazy cool.
did it well.
I'm pretty excited to tell everything.
Yeah, it's a total state.
No, I was close to understanding that tensor stuff. Like, it's like a metric.
Metrics is
Yeah, like it's a vector.
I'm going to think
Keep
about
it
it during the January, yeah.
If not, I'm gonna steal it.
Oh, wow.
I also started with the theft has already killed.
Yeah. So nervous. We also have that point on economics. There's also the
Very nice talk. Very, very interesting.
I took like shit ton of videos, so I'm just gonna send them to you. Like there was like 10 different angles of like videos. You know. I hope I know.
Maria, Jacob.
Yeah, you look good. You look good. You also like don't have any like problems or anything.
It was
really good. It was really good.
We've got a lot of videos.
Yeah, me too. I hope I look good in those videos. Perfect. Why are we here? You gonna come study or are you gonna go drinking?
I don't know. I'm done. I have to finish this paper and that's
Paper as well?
I have a paper for this. And then actually I'm going to plot those differential equations and in the plot how the universe is expanding our video.
It's gonna the rest of my life. Listen, I solve Sudoku every day.
You can definitely add this to
It's not for you. Yeah, it's just I don't know my phone or I don't know. No, really. Just, just practice. It's like inventing MCS problems for students. Really good job. Thank you so much. How long did it take you to read that?
Like I was pulling in liners. So.
Do you study something like that in your classes?
It was so hard to actually understand those. But like,
Well, yeah.
like this is things in my which is
And you need to.
I mean, so the main idea of that is how basically how the
Because
universe
it's
expands.
not an application. It's you ask the professor and they'll
It's just wonderful how people came up to this, you know.
I haven't asked him yet.
Huge
but
respect
I'm gonna
to
wait
those.
until like the end.
so hard.
Ask him after the second semester.
Yeah. But you know, the question about practical, it's interesting because you never knows. People never knew how to apply imaginary numbers when they invented it. You know, it was invented 18th century or something like that, or even earlier. The guy invented it because the math don't work, right? But then they realized they could apply it in electrical engineering. Like it's everywhere in electrical engineering and so on. So you never know.
I'm 100% being.
Maybe.
C.
So No. You have to wait. Like, science is, I mean, the beauty of science is that you work on something that may not have the value today, but will have the value in the future. That's the beauty of it, because the engineering you apply it now, you apply it now, but the science
most likely gonna become C.
you develop something that can be applied later, which is good. So yeah.
Have an answer.
Thank you.
Yeah, I'm planning on becoming an algebra.
Outside this.
Algebra. Ah, bro. Algebra is second math major. Cool. Algebra. It's like wow, you know.
Like my presentation.
Like here, it's very limited because two TAs.
Please, please.
Start.
So you're not going to know, like, sorry,
Your rhythm and just continue and
and for some reason, it's like even following this, they have to take complete breaks. So basically, there's only one person that can be taken. Think about it that way.
Please, Manny. I have no words.
No, for the other person. Because you're not HD. So like you're competing against all the rest
I mean, you texted me last night about this.
and all CS. And they're
I mean, like-
only one person. Anyway, it's okay.
I just love this.
That's how it works for much tricks as well.
I think you voted for the one you've just started embracing.
So my mom just
It's not an insult.
it's not.
I mean,
Yeah, in French it's literally.
physics majors, that's not an insult.
No, it's literally. Like exactly this, it's literally.
Second year.
I know.
What are you saying?
I thought it was a theory.
Actually told me to do study it. I'm like, what?
I'm using the Tongs lecture notes.
Oh my god.
They're so nice, he's so witty.
Merci. Teşekkürler.
Professional depreciation. When you ask a person what is lattice, people think about this. When you ask computer scientists, people think of
Please,
Let's stay there and chill like the last of us.
Of course.
Tanya.
Pretty motivation, right?
It's really addressed for the electromagnetic part of model.
Ciao.
Yeah, thank you. No. No.
You read that?
Please. I beg you. Actually,
No, just say one sentence.
no. She's perfect. She's the one.
You do this.
Guys! So again, so we start our third talk and the last talk of the day. So please take seats and be ready. Because we'll now start the last talk of the day that is given by Tanya about Kuta methods and their role in modern neural networks.
Hello everyone, I'm Tanya and today I am presenting about the Ranjikuta methods and its use mostly in the neural networks, which is today very popular in the chat GPTs and all that because everything is done in the backend is all about same. So let's move forward to it. So first of all, I would like to present you some foundations and the basic needs. So it is mostly common use in the differential equations and other stuff. And would like to tell you what is the power of it. So it is mostly used in everywhere now. As I mentioned, the ChatGPT is taking over everywhere. So neural networks are getting more and more important. And the use of it in the neural bodies is getting popular day by day. After that, the core behind it is that if you see this graph, there are different lines and scopes. So this means that Ranjikuta has a kind of steps in which it takes different slopes and make the average of it to find the accurate and precise answer. Instead of the Euler method, which is the previous one used by the mathematicians, it was just one and giving a very unprecise answer. Instead of just giving an exact answer, there was a difference of 10 to 15% in the accurate answer. So instead of that, this method is more precisely used, where you can see that different slopes are taken. Like here you can see 4 slopes and the average of that is taken for the final answer so that we can get exact, precise and final slope. Then it is the structure, and of course before getting the final answers there are many different kind of mathematicians doing the same way. So this is another by another person who is the Brusha Tableau. He also tried to do something in this way, but not with the graphs, but the table. So it also concluded the same way that the formulas which he used were same coming, which is used by the Ranjikuta. So this is the RK2 algorithm, which is the RK2 algorithm, which is the main. Oh, sorry. which is the main formula of here. It has the main first two formulas, and then the main requirement is this conditions which we need to satisfy before solving this method, and then these are the two formulas which are first used, and then this is the final step where the four derivations are done, and then the final collision, and then the fourth accuracy order is precisely answered. Yes. Now is the sequential slope equations where I mentioned that slopes are needed the most. So here it is mostly described why it is needed, and more each stage is involving a derivative acting a layer, as the derivation is described by the slope, as we all know that. Then yes, the importance of it in the neural ODs. Like as I mentioned, the chat GPTs and all that stuff is taking differential equations are more needed in the backend, and the stability, sorry, the stability it provides is the precisely, and the required needs are completed with this. And of course, whenever we are doing something, the costs are also concluded. So whenever we use this, the heavier mathematician, the cost is reduced, which makes it more accurate and easier for other people to use this. Then there are the learn methods, like now we are providing something to neural networks. So we have to provide some information to them. So when we are providing them information, we don't give them some fixed numbers. We give them freedom to choose and find the values, which give them more exact answers. So what's that written here is that they are no longer fixed, but they're trainable parameters. Like they are being trained at the back end, and then they are given the values on their own instead of just giving a fixed value. Okay. So then there are some constant preserving and you have to solver coefficients, as the previous thing is interlinked with that, because the things which are coefficients are these. This is the same coefficient which is talking about here. Then, as during my research, I also came across some experiments and some experiences from the past mathematicians. So this is one of them, which is the circular orbital prediction, in which they had gone through a lot of research, and they concluded that this thing is also following the same method, doing different steps and concluding the same easier way in the final end. So I would like to focus on these some definitions which are very basic but are easy to learn. It's most talking about the RK2, which is the mid derivation. Like if they are taking 4 steps, the second step is known as the RK2. And as I mentioned previous, the formulas, it is the same thing which I mentioned earlier. Now, it's about the Ranjikuta. Why did they switch to Ranjikuta instead of Euler method? So why they switch is that the long-term accuracy. The more they do the steps, the average comes to the precise, to the accurate answer, instead of just giving an error and the different problems. So the error accumulation is the higher, and the system specific, like the time used, is low. Okay. And of course, everything has some cons and pros as well. So this has a disadvantage that it takes a lot of time to cover the answer instead of just taking it in less time as the Euler is. But as I mentioned, it's take the final answer more correctly. So this is the most limitation of it, that it has to take a lot of time, a lot of calculations, as it has more higher graphs and more higher calculations. So which it is still working, and the researches on it are still going, and it is already under construction. But the thing is that it's better than Euler, and that's what I wanted to mention in my research paper as well. That why neural networks people are using more Ranjikuta than the Euler is that all because the accuracy and precision is more taking priority than the just taking the time as a music precision. So as we also say that that the accuracy is most important in most of the things. And yeah, thank you for my speech. Any questions?
Shukriya.
Thank you. Any questions? Yeah.
So I have one question. So at some point you said that rational decompression is faster than Euler, right?
No, it's not faster. It's more accurate. It's faster. No, that's the only limitation I talked about. it is the only limitation which we have, that it takes more time, but the more accurate answers. Anyone else? Okay, thank you.
So that's the end, right? So this will be, let's say, an end of this semester. Thank you for all people that came here. Thank you for all people that attended this event. And be ready, because exams are coming, of course. But also be ready for the next semester, because Math Society will come with even greater stuff in our next semester. So thank you very much, and have a nice day.
I might join, yeah. I might join. There. So good. No, see?
Look at this.
Not looks that's what I'm gonna do.
It looks scary.
Bro, I will.
Anyways.
Yeah, I think I got lost.